Hi, welcome to module number 36. We're going to be covering basis expansions. So recall that we've been discussing linear models quite a bit, and that's in part because many things are approximately linear. Many real-world systems over the last 200 years or so, because there's been a lot of mathematical and algorithmic understanding of linear approaches. Hardware has been developed to acquire things in a linear way. And a linear approach really can be considered as a first order Taylor approximation. Some of you, when studying analog circuits, may have been using these types of approximations. And it might be difficult to fit more complex functions when the number of observations is smaller. Also, when the dimensionality is large, because when the dimensionality is large, we need a very large number of samples n in order to fit complex functions. However, having said that, although nonlinear functions are complicated, real-world functions, real-world data often isn't linear. So we may want to augment our models, augment meaning add to our models. We begin with a vector of inputs, and then we augment or replace the inputs with a transformation of x. So x could be p-dimensional, and then hm of x, m for the index, a new function h at index m as a function of the p-dimensional vector is going to take us from rp to r, meaning that it's going to be potentially a nonlinear function, and it's going to map to one dimension. So once we have capital M functions in total, we can form a linear basis expansion of those capital M functions. F of x will be a summation over lowercase m, the index, beta m, the coefficient, multiplied by hm of x, the transformation. And we fit the parameters beta m to these capital M different functions. Now, why is it augmented? Why did we increase the number of terms? So we started perhaps with the p terms corresponding to the p dimensions of the raw data, and we start adding more and more terms, and capital M, the total number of nonlinear transformations, might be much larger than p. So here's an example. Take h of m, hm being equal to one of the xm's. So the first for m being equal to 1, 2, up to capital P, or lowercase p, whatever notation you prefer, those initial functions are the original data, the linear data. Then we can add perhaps quadratic terms. Quadratic terms meaning that hm of x would be the jth coefficient squared, or maybe xj multiplied by xk, where j and k are both elements in the set 1 through p, and presumably j is different from k, because if j is equal to k, then we've already discussed the quadratic terms. Now this sounds perhaps helpful, because now we have more flexibility. We have these nonlinear, these quadratic second order terms. However, the number of such terms grows quite a bit. So here, for example, the number of quadratic terms, I'll just call it QUAD, is p such terms. And the number of cross terms of the form xj, xk is p minus 1 over 2. Or perhaps p plus 1. Okay, you know what? Let's just call this approximately half p squared. Okay, easy to remember. So overall, the number of second order terms is theta of p squared. You know, that is not controversial at all. And if p is 10, then half p squared is not too bad. But if p is 100, p squared is starting to be quite significant. we could also move to piecewise polynomials, splines, which we'll be describing in upcoming slides, and other types of nonlinear expansions, even sinusoids. But you may have a lot of them. You may begin with p equals 100, and you may end up with many thousands, even millions of these nonlinear functions. And we don't want to have a situation where we have a massive amount of possible functions in our dictionary, and then just by just having a massive number there, some of them look quite similar to our data. So we need to somehow control the complexity or regularize, meaning by regularize, meaning we don't want to allow our coefficients to be a ton of small non-zero coefficients. Instead, we would prefer them to be sparse somehow. We'd like to perform some type of variable or subset selection. So now let's try to visualize this. One approach is to use piecewise polynomials. So instead of using very complicated nonlinear functions for the entire range, we split up the range into several parts. So let's say from 0 to psi1, and from psi1 to psi2, and from psi2 to the end of the data. And for each of them, we could give a piecewise constant type of fit. So this would be a constant, the green, a second constant, a third constant. In every range, we have a constant. And overall, the true function would be the blue. And in each of the ranges, the green is somewhat okay fit for the blue, but overall, it has these jagged discontinuities. And a piecewise fit is good for the local structure, but there's quite a bit of problems between the different ranges. Now, maybe instead of piecewise constant, we want to use piecewise linear, that in each of the three portions of the range, we have a linear function. Once again, if by chance the discontinuity between two of these piecewise linear functions is moderate, maybe that's okay, but here it's not going to be quite so okay. So maybe we want to enforce continuity. So one way to do that would be a continuous piecewise linear fit, meaning that at these 2 points we require things to be connected. But when we require things to be connected, when we constrain things, that reduces the number of degrees of freedom. Another popular approach is using splines. So splines, you can read about them in the book, but the bottom line is that there are some polynomial properties involved, and they fit well within regions. So one possibility, again, is to allow discontinuities between the 3 different regions, and you can see that the discontinuities in each of the regions, we may fit the data rather well, as in this region. However, the discontinuities between the region, they may be quite severe. And if we enforce continuity, things are somewhat better. Then again, you can see that the slope is discontinuous. So what you can see, for example, in the discontinuous example, is that by fitting the data well within each region, we fluctuate more between regions. And instead of having a continuous type of requirement, where again, the slope, there may be a discontinuity in the slope, we may impose another constraint that the first derivative is continuous. And then here and here, the function looks better. And imposing continuous second, third derivatives, etc., gives closer and closer fits. So overall, these type of approaches, they support multidimensional data, wavelets are another possibility that can be used, a lot of flexibility. Finally, here's a discussion of a real-world application. Recall, several weeks ago, we discussed a financial example. Some of the terms in X could contain financial data, prices, how much the market is pricing different companies, their profits, their sales, their research and development expenditures, various raw data. And then there could be a linear model for future prices that might be a bit restrictive. And we might augment X with other basis functions perhaps quadratic terms, cross terms, splines, sinusoids, you name it, and this might overall give a better fit. So that's it for module number 36, and we'll continue next time.